Yeah, so that's exactly right. What we're talking about now is dealing with cars. That's exactly right. I mean, I think that's the best illustration to understand this. Not necessarily what you're to see in the book, but scope out this nerd style Desmos that I made. Notice that in this particular illustration, I hope you see the connection here between linear and rotational motion, because what we're studying is relative motion analysis. And what I want you to notice, I called one the driver and one the follower. Do you notice that the blue radius, if you will, is spinning at a constant speed? So that's the driver. But then because there's that green, what is that, a crank arm? I can't remember, connecting rod. Because there's a green connecting rod to it. So think of that blue as kind of like an electric motor. So it's spinning at a constant speed. But because of that green connecting arm, notice that follower is kind of moving back and forth. But what I want you to notice is just watch the orange dot, and I want you to consider how fast it's going. The blue is going at a constant speed. Is the orange going at a constant speed? And yeah, where is it the fastest and where is it the slowest? You notice that's kind of an interesting conundrum. Let's see if I can control this a little bit. Ooh, I can, but it's really sensitive. Let's see, can I do this with a pen? Sensitive. It's very sensitive. That's too sensitive. It's jumping too much. The step is too big. I mean, let's just leave it at that for now. It's okay. Since I can't control it. So yeah, oddly, even though the driver is a constant, and notice the only way to measure the driver's speed is by angular velocity. You can't really measure it as a linear velocity, and yet that, thanks to that green connecting rod, there is a linear velocity. But even though the angular velocity of blue is constant, the linear velocity of orange is not constant. And yeah, it kind of does look like the center is where it's fast. Do you notice it really slows down right at A and B, incidentally? So that's kind of interesting. So the connection between these two. Now, I won't take the time to redo this, but I have an entire other one of the same exact picture, except for the piston is the driver, and that's how a car would work. In a sense, the explosion in AB, the piston would be linear velocity, and it's going to shoot that, when I'm here, I'm calling the follower out. And then that's going to be connected to the, circular wheel, if you will. And then it's going to, the same thing happens there, in the sense that a constant speed with the orange actually produces a totally different rotational speed. Kind of depends on where you are. So if I said, hey, look, the blue, in this case, what we're looking at here where the circle is the driver. If I said, hey, look, that angular velocity is, 2 radians a second or something like that. And I said, what's the speed over there, for the follower? You'd have to say, well, when? Because the speed's different all the time. So you're going to be given problems here where there's kind of an instant in time. And so the motion of one thing is connected to the motion of something else. That's really what this comes down to. And again, in our culture, turning linear to rotational speed is the backbone of just so many of our cool machines. So we want to see if we can understand this. Unfortunately, it's not simple. So let's see if we can figure this out. Let's see. I know it's just a machine, but it feels like I should turn it off so it can rest. Okay, so here's the deal. Here's the thing you gotta get down. Actually, maybe I'll show you one other thing first, just because it's fun. I hinted at this a little bit the other day, but this is just a page I made that's kind of cool. Sounds like from the other day, you guys already understand the concept of how 4-stroke combustion engines work, but I just want you to kind of stare at that a little bit. There's an animation online I was kind of lamely looking for the other day, and it wasn't a very good one, but this particular animation that I have sitting there on YouTube is real cool. So I guess all I want to know is, do you see the same thing here, in the sense that, I'm looking at this piston right here, and bam, it's connected to this connecting rod, but do you notice it's actually not connected like at the center of it? If it was, that wouldn't allow any motion. But since this is connected kind of at a distance right there, can you picture that's going to kind of go around in circles? and that connecting rod is going to kind of bounce back and forth. So it's just kind of cool to know the terminology, but piston, connecting rod, crankshaft. In the end, the piston moving thanks to the connection rod is going to cause the crankshaft to rotate. And then you can see the gear over there on the side, and that's going to work its way back through just like the gears on a bike in a sense, back to the back of the car. And I'm not a car guy. So earlier in my life, it's like, oh my God, that's why it's called a V6, because the pistons are shaped like a V and there's 6 of them. It's like, it's a world of mystery. Or like you flush the toilet, where does it go? It's magic. I don't know. It's like to understand like how the world works is my favorite part of engineering. And I have an old 65 Chevy pickup that I sold recently, but it's a straight 6. And it's like, oh, straight, like not a V. Aha, I got it. This is a flat 4. That's kind of cool. The pistons don't have to necessarily be lined up any particular way to create this kind of motion, but it's just kind of fun to think about engineers playing around, trying to get something like this to work. And of course, it's most manifest in a steam engine, just because that's where this all started. And you can actually see all of this stuff kind of working. It got more complex as time went on, but that's just it's kind of important to understand, I think. Awesome. And then of course, in this picture right here, here's the piston, that explosion right up in there is going to happen. That's going to push down. When that pushes down, this is going to have to go rotating in that direction. So the one thing I want to make sure you understand, because of the figures that I drew, it's in a sense, there's kind of a circle right here that is going to follow. It's not that there's anything there. It's just that point right there is going to traverse around in a circle around that center point right there. And of course, that rotation, rotating this green gear down here, if you will, that rotation is what we're going to kind of capture and do something with. Okay. All right. You ready? Let's see if we can make something happen here. Okay. So here's the key. How in the world are we to understand this? Here we go. Relative motion analysis. And today we are only going to look at velocity. This is so complicated that we can't even talk about velocity and acceleration in the same day. Not only that, we might even finish velocity today. And velocity is challenging and acceleration is even worse. So what we're going to talk about is just how's the speed of one going to allow us to figure out the speed of the other. That's really what it comes down to. And so let's consider this. Pretty good circle. I like it. Okay, so I got this point over here that I'm going to call A. And we're going to think of this as the driver this time, because this is more like the piston of a car, and I think it'll make more sense to you. And let's give it a velocity here. So rather than put a number to this just yet, I'm just going to say that has some kind of a velocity. So explosion goes off and that point moves. And of course, that has nothing to do with the circle until we say, yeah, it does. Let's go connect it. So now all of a sudden we're connected. And so again, what I'm modeling there is really, I don't know if I'm going to save this or erase it, but we're really talking about, some kind of a crank arm here. I'll draw it sort of wonky a little bit. It's not so much that the blue circle exists, it's that it's connected to that crank arm. Is that what it was called? Crank arm? By the connecting rod. And then that red dot, if you will, is going to follow that circle, if you will, as it goes around. And so, okay, cool, that makes sense. So what we're interested in is what's the velocity of B over there? Now, here's the hard part from things we've studied earlier. What does the velocity of B over there look like? How you doing, Ian?
Good.
Looking studly as ever, man. What is the velocity of B? Given that B is forced to travel in a circle thanks to the crank arm, from our circular motion discussion, how do you even measure the velocity of B? Does it make sense? It's not linear, like it's not moving through space. What is the velocity of B? Do you have an answer to that? Yeah, there's two ways of looking at it. There's this angular velocity right here, which we might call, and I'm gonna actually give this point a name too, C. We might call that omega, which is the angular velocity. And notice based on where I have this drawn, do you agree that it's rotating that direction, which would, I guess we'd call clockwise? So it's in the position I happen to have it drawn, that pole is gonna rotate it clockwise. So we can talk about the angular velocity of it. If we were to actually talk about just straight the velocity of it, does it make sense it was this? That's actually the velocity of B. And notice, how did I want to draw that? 90 degrees, that's exactly right. Thank you for reading my small mind, Thomas. That angle right there is 90 degrees. And so the velocity is always perpendicular to the circle it's on. Earlier in this class, we studied that it's on a circle always, even if it's traveling in some random motion. It's just that the radius of the circle is constantly changing, but this is like constantly a circle. So that's actually the velocity of B. So we've got sort of the angular velocity of, I could even call it BC if I wanted to, the angular velocity of B as it rotates around C. But we can also talk about the linear velocity of B. And remember, those are related. We had a formula about that. It was like radius times angular velocity was linear velocity or something like that. We'll look it up again. And so the real question is, the real question here that we're trying to answer then today is going to be like, given a velocity of A for today's problem, let's see what's the first one we're doing. For today's problem, velocity of A is going to be 3 feet per second. So I'll just go ahead and start with that. Like 3, if you were given a velocity of A, 3 feet per second, of course, you got to know some dimensions here, right? You got to know the radius of CB and some other things. The question is like, can we find the velocity of B just as a linear velocity? So how does the velocity of one thing connect to something else? Relative motion analysis. I know the green velocity. And so relative to that, what's the red velocity? And ultimately both velocities. What's the angular velocity and the linear velocity at that point? How does the explosion in the piston affect this crank arm? Therefore, how fast is my car going to go down the road? Now, here's where it gets hard. Woo! You should stare at that and go, God, I have no idea. Like, that's totally confusing just to stare at. Like, how are those even connected? Like, do I make triangles out of it, right? Triangles and things of that nature. Well, it turns out to be a little bit more complex than that. And this is the answer to that question. So watch this. If I said, well, yeah, the velocity of B, that's not hard to find. You just say the velocity of B equals something to do with the velocity of A. So let's stare at this for just 1 second. So I drew velocity of A over there as this kind of little green vector, and I want to do the same thing up here. Does it make sense? Kind of that's not really true. Like if velocity of A is connected to that red connecting rod, then wouldn't that connecting rod just want to slide to the right? So I came back here and said, all right, let it happen. Isn't that where kind of A, B would want to go? In a sense, you could say, okay, B just moved to here, that'd be B prime, and A moved to here, that'd be A prime. But of course, that can't happen, right? It's not going to do that because B is hooked to that circle. Like it can't do that. You agree with that? But that's what linear velocity does, is it wants to move something kind of in that direction, if you will. So you can't really say like the equal sign that I wrote down there doesn't really make any sense, right? Velocity of B equals velocity of A. What are you talking about? It makes no sense. Well, after that happens, like this is what's happening just microscopically. After that happens, this is what happens next. Then, although B can't actually ever get away from the circle, does it make sense that then it could be thought of as rotating into position right over there, almost like First B goes out to B prime, and then it rotates down to B double prime, like into its next location. So actually the velocity of B is found by first what mathematicians call a trend. You don't need to know this word, but just because it's cool. First it translates, which actually just means a motion in one direction. There's actually just two kinds of motion. There's translations, which is you move from one place to another. So B goes to B prime, moves straight out there, makes total sense. Secondly, though, there's a rotation where the velocity of B prime, in this case, as it rotates around A prime. That's the second thing I drew there. Does it make sense? So first B went to B prime, translating, and then it rotated. Then there was a rotation back into position. So the trick to this is this motion is so complicated, you have to be smart enough, and I'm not smart enough to invent this, but I am smart enough to read a book and figure it out afterwards. What you have to do is break it into two things we do understand. That motion is so confusing that left to itself, we just sit here for weeks staring at it, not make any progress. But if you first think of it as a translation, B moves to B prime, and then you say, oh, well, that you can't actually be out there. Well, then let's rotate it back into position. So actually, you can think of it as like, yeah, B just kind of went down this way, didn't it? So we're not going to let it go as far as what I just drew, but think of it as moving like a millimeter. It moved out a millimeter and then it rotated back into position, out a millimeter and back into position. The point is, we actually do understand those two things. We understand linear velocity, we understand rotational velocity. And so I just broke this complex motion into a translation and a rotation. And that's kind of what's happening here. And that's the thing we got to make sense of.
B prime being parallel with C, like why is it going at an angle and not just straight out?
Because it's hooked to that connecting rod. And since A moved directly right, then B has to move directly right. At least theoretically. As we said, it can't really move out there, right? It's stuck. B is stuck on that circle. It can't do what I'm just describing.
I guess when I think like you spin a ball, get a circle, and let go of the ball.
Yeah.
It goes exactly in that direction. So wouldn't that just be a straight line from C to B prime?
From C to B prime. From C to B prime, you're saying it'd be a straight line. Not following that just yet. Yeah, so my interest in, let's just keep talking. Keep formulating your question, keep asking it a different way until I get what's kind of on your mind too. Can you see if B was allowed to do this? Like, because remember, there actually isn't a circle there. Does that make sense? It's just it's representing a path that you could keep B on the circle if you let it do those two things. I would have to be away for a second, rotate back in, be away for a second, rotate back in. But you see how that the combination of those two motions, basically linear and then rotational. Like I do understand those. And that's actually how to figure this out. I literally let it move out there and then I let it rotate back into position. And in that way, based on this basic formula, I'm going to be able to figure this out. Now, the way it's written down is without the primes. In other words, this is going to be kind of our base formula right here. Now, and we're going to be able to get these problems right using that formula, even if you can't conceptually make sense exactly of what I'm saying. Now I'm going to keep doing this again, because as always, my interest is actually that you get a conceptual understanding of this. I doubt you would ever be doing this in any kind of an engineering context, just based on computers and so forth and kind of the way the world works. Now, in order to do that, does it make sense that this, I don't know, this dotted line out here is also, as I said, having to rotate, and isn't that effectively a rotation of B prime as it rotates around A prime, so to speak. So there's actually an angular speed. In other words, that red crank arm is having a rotational speed too. So in the end, it's just kind of cool to figure out all we're doing is connecting this system up. We're giving a velocity to the green A point. And then we're just saying, you know, what else happens as a result of that? And so we're going to have this angular velocity of that crank arm over there. We're going to have this angular velocity that results in that connecting rod. And then we're also going to have a linear velocity here. And it's like, it'd be kind of cool to figure all those things out. In the end, that's what this class is about, right? It's like, figure stuff out. You do one thing, what happens? You got to understand that ahead of time so we can either not let it happen or take advantage of it. In this case, we're going to take advantage of it and try to make a car roll down the road. So A is the driver and B, if you will, in this case, is the follower. And those highlighted calculations are what we're going to be able to make, what we're going to want to be able to understand. And as I said, the most important one is probably this angular speed over here, because that's the kind of thing that sort of directly ends up connected to the car, right? I don't know as we super care exactly what velocity of B is, but because of the formulas we have, we're going to need the velocity of B in order to find that. And this formula right here is telling us how we're going to get the velocity of B. So the velocity of B is going to be our introduction to all of this. It's not our final answer that we want to know, but we can actually calculate it based on this logic right here. And then we'll convert it to that angular speed. And so in the end, we're saying, how does this linear speed over here create angular speed over here? That's kind of cool. And I'll just write this down here since we're talking about it. But the other day we basically said, yeah, linear velocity can be turned into angular velocity by just taking that angular velocity and multiplying it by the radius, as long as we know the angular velocity was in radians per second. So that's how we convert between angular velocity world and linear velocity world. All we need to know is the radius. And we do know the radius. That CB over there will have to be something we're told or something we know in the problem. Okay. Ouch. Painful. All right, let's do the first problem and see if we can apply it. Now I tried to draw, if you will, the simplest picture I could. I put everything in the simplest location I could, and I even drew it kind of like a car in the sense that you see the piston up there and those angled lines are indicating it's kind of stuck in that shaft. And notice because it's stuck in that shaft, it basically can't move up or down. It can only move right and left. So that's just like a car. So I put this 3 foot per second speed on A. And then and notice that down here, because I used AutoCAD, I drew a dotted circle, meaning there's not actually a circle there. It's just going to follow that. So BC is the connecting rod. I'm sorry, AB is the connecting rod and BC is the crank arm. So, and notice I gave the velocity of A to the right. I could have given it to the left. So can you reason out what's going to happen to B then? So if it's sitting there and then you suddenly say, all right, 3, go. Do you agree that this point is going to want to start going in that direction then automatically? I mean, that's not hard to see, right? So of course, I'm just interested in, you know, what's happening over there. How's it all going to go? And so notice I asked, find the angular velocity of links BC and AB. And notice I said at the instant shown, because remember what I showed you in that little animation that I showed you in Desmos, that it kind of depends. If you want to know speed, it depends what time it is. And so at the instant shown, and I said the instant when that angle down there is 40 degrees. And then I gave you some, you know, some geometry here. BC, the crank arm is 2 feet long. AB, the connecting rod, is 7 feet long. And then I gave you that initial velocity. And so the 40 degrees and the 2 and the 7 is enough geometry to kind of allow you to see, oh, I see how those are connected, if you will. All right. So let's see if we can survive this. So we said The backbone equation here is that the velocity of B, the follower, is found by just taking the velocity of A, but then adding to it the velocity of B as it rotates around A to get back into position. Now I'm going to erase all this because it's going to make a mess of this drawing. But again, I want to redraw what I just said a second ago. I want to redraw what the equation that I just drew there. I want to redraw what that looks like. What does that mean? Well, if we first say, come on, man, you can write. If we first say, we first apply the velocity of A, then would you agree A, if you will, moves in that direction a little bit? And so if B just does the same thing, the velocity of B is the same as the velocity of A. So if A moves right, then B moves right too. So now B moved to there. Do you agree with that? A moved right, B moves right. If you want to know what B is, see what A did. A moved right 3. Okay, B moves right 3 as well. So if you will, A is now here, B is now there, and therefore the connecting rod, it's in that position. But now we say, well, that can't happen because B actually has to stay on that dotted line. So the question is, do you see the rotation of A prime, B prime? Do you see what rotation it would have to make to get back on the circle where it belongs? Remember, these things are actually happening simultaneously. You can't even see it. They're happening instantly, both. So do you see that in order for B prime to get back onto A, and I need you to see this circle really clearly here. Notice I'm trying to draw a circle that's centered over here around A, because if that crank rod, if that connecting rod AB, A prime, B prime, is rotating around A, isn't it going to rotate in a circle around A? So do you see that, if you will, it's going to rotate in this direction to kind of get back on the circle, and so that would be B double prime. That's like where B went. So basically, first I went to the right, and then second, we rotated B around A, really B prime around A prime in my picture. We rotated B around A, and then it got back into position over there. So we broke the motion of B into a translation and then a rotation. So end result is it really just went like that. So this is calculus again. Calculus is, that's microscopic. It can't, what I just showed can't happen, but it could happen if we went a billionth of an inch, right? So notice it's interesting that it actually rotated, it moved right. I guess you might say it sort of moved in the positive X direction first. And then it rotated, but how did it rotate? Let's see, I guess we call that a negative rotation, didn't we? Like a negative rotation. Just reasoning this out, a negative rotation around A, and then it landed back on the circle where it belongs. I'll leave that there as long as I can. All right, how do we do this? It's not terrible. We've got to consider this horizontally and vertically, as we often have in this class. The confusion of all of this in 3 dimensions is taken away if we just say, well, what happened in X and what happened in Y? Let's work it in terms of the coordinate system. So I'm just going to rewrite this equation. Velocity of B equals velocity of A plus the velocity of B with respect to A, except I'm going to say we're talking about X's, only X's. We're only interested in X velocities. Yes, I'm kind of using the standard clockwise is negative. So you just need to picture it, I guess, is all that's really involved. Okay, so now I got to put other stuff in here, so I have to disappear all this stuff. So let's fill in some stuff. So ultimately we said B is really, the velocity of B is actually in that direction, right? It's perpendicular to the circular direction around which it's going, that's actually the direction it is. Secondly, I don't know if I should have drawn this in before I erased that last one. Can you also see that perpendicular to that connecting rod, this would actually be the velocity of B as it rotates around A? It's always perpendicular to the axis around which it rotates. So it slides right first. Remember, velocities are always perpendicular to the radius they rotate around. So do you agree that that's the velocity of B with respect to A? In other words, it's perpendicular to this radius right here around which it rotates. And we saw that it was going that direction. Does it make sense? How do I know what direction perpendicular is? Is it that way? Well, based on the picture I just drew, that's not the right direction. That's not the way it just rotated. Do you agree with that? And based on the picture, I didn't draw the velocity of B going in this direction. I didn't draw it that way because of logic. So it's kind of helps if you can actually reason out what's happening here. Literally kind of draw in the stuff that I drew in. Let me give you one more pass at that. So we said first, B follows A and slides to the right. But then in order to get back on track, doesn't it have to, well, rotate in that direction? 90 degrees, like isn't velocity always perpendicular? Now it's, it's rotating angularly, if you will. But that's how it gets back into position right here. Does that make sense? You see why I drew that orange velocity of B relative to A, 90 degrees to that? It's rotating around that red crank arm. We got more than one problem to do, and so you'll have time to see if you can get your mind around it. But that's the two things I got to draw in here. Now, that's great, except for notice that's velocity of B and velocity of BA, not velocity of BX, velocity of AX. So those aren't, I can't plug those into this formula. But let's stare at this a little bit. If we agree that this is 40 degrees, then since the blue 90 is there, then wouldn't this angle be 50 degrees right here? And then since the orange 90, isn't this also 40 degrees over there? So thanks to the snapshot in time I was given, I know all the angles in that picture. And so because of that 40 in trigonometry, can I convert those blue and orange speeds into horizontal and vertical? So we interrupted us. I thought I turned that off. That would not happen. It's weird that somebody 55 couldn't operate a cell phone. Don't you think that's weird? Old people don't work technology very well. So take a look at the things that we know. Now I want you to stare at those blue equations, if you will. Velocity of BX, velocity of AX. Do I know any of those? Any of them? Well, I'll start with velocity of B in the X direction. Take a look at that vector B there. It's rotating, it's aiming straight up. If that's the case, how is B moving in the X direction? It's not. Does it make sense? Right now, it's going straight up. It's not going at an angle. It's going straight up. Therefore, this is actually nothing. Now, had I put B in some other location, do you see what I mean? I put it in a really nice location. If B was over here, so that it was rotating in that direction, does it make sense? It has a component in Y and it has a component in X. Does it make sense it would have that? But because of where I just happened to draw this, it isn't moving left and right at all. Basically, every other place in this picture, it's going to be moving left and right. But here it just moves up. Again, we have more than one example to try to make this go into your brain. What about velocity of A in the x direction? What about A? Yeah, notice it's in a shaft that is perfectly horizontal, and so it's forced and it's going right. We typically call right positive. So, whoops, thank God for the undo button. So that's 3. And so velocity of BA in the x direction must be -3 then. But let's do something even a little bit more creative. Do you agree that velocity of BA, because of the way it's aiming, do you agree that this is its vector in the x direction? And this would be its vector in the y direction? Since it is at some weird angle? Now, because of the way I just drew that, I think I'll even go one step further with the angles and say, well, because that last one is 40, then that makes this 50. So I can say, well, velocity of BA in the x direction would just be velocity of BA, but modified, I guess that'd be by the cosine of 50, wouldn't it? You agree with that? And by the way, notice it's going left. Therefore, I'm even going to call that a negative number. So instead of just saying, oh, the velocity of BA in the x direction is -3, I really didn't want to know it in the x direction. I actually want to know the velocity of BA. So I guess that would mean the velocity of BA cosine of 50 would be equal to 3. Does that make sense? So that everything equals 0. So if I take 3 and divide by the cosine of 50, I actually get the velocity of B as it rotates around A, and I get 4.67 approximately. So that feels like, I don't know if that's the answer to anything, but it feels like, hey, I just figured something out. That's a good question. What's your thoughts on that? Remember that what we just did is translate it from rectangular to rotational speed. And rotational speed was always called positive in the direction it was going. In other words, this is a positive direction right there. This over here would be a negative direction. So it's not left and right anymore. Does that make sense? In other words, let's say this particle is like flying along this weird line right here, and it's like, hey, where is it? Oh, it's right there. Then we said automatically, well, that's its velocity, and we said that was positive.
You set the x component of BA is equal to velocity of A in the x direction. With that, BA cosine 50 is equal to 3.
That's right. So go ahead.
And this is just right, if that's going, well, A is going this way.
Yeah, A is going to the right.
And then the x component is left.
That's exactly right. But remember, that's because, and this is the part that's confusing about this, that's because first it moved there, like first velocity of A happened, and basically this thing went straight to the right, but then it was forced to rotate in this direction to get back where it belongs. And so as a result of that, it actually is going left, literally is going left. So again, it doesn't look like it, right? Like and I totally see what you're saying. You're basically saying, hey, this thing is sitting right here. It goes right there. Well, that's going right, isn't it? It's going up and right. But the problem is, we can't think about this all in one pass. We have to actually break it down into those two motions. We have to let it slide right green and then rotate back into position. If it does rotate back into position, then it is literally going left and it's going up in order to get there. Isn't that weird? Excellent question. You always ask great questions. So this is painful, right? This hurts. This is really hard to kind of get your mind around. Now, let's just stop there and notice something we figured out. A second ago, I reminded you that the velocity equation can be found by taking the rotational and dividing by r. So since we just found this velocity right here, this linear velocity of b as it rotates around a, then I could say that's equal to the angular velocity of b as it rotates around a times the radius of, well, BA or AB or whatever. And since I was told the radius of AB up there was 7 feet, then to find the angular velocity, if I take that 4.67 and I divide by 7, I get that angular velocity is 0.67. And notice the units. Feet per second divided by feet would be nothings per second. So this angular velocity is 0.67 nothings per second, which, because nothing sounds weird, we call radians. But notice we just figured out the rotational speed of that connecting arm. Isn't that kind of cool? So linear speed caused that thing to rotate. Now let's see, let's think about that. Is that positive or negative? If I want to be technical about it. Because I go back and forth between like creating some kind of a sign convention versus just using my logic. In one respect, I don't think it matters. Like, who cares what direction it's rotating? But as I showed you a second ago, first it goes here, and then it actually rotates that way. Well, don't we usually call that a negative rotation? Because clockwise, as it rotates around this point and goes that direction, we call negative. And if it had went counterclockwise, we call that positive. Technically, I think I should say that's negative. I don't really care, but that's just kind of good to think about, I think. How's your brain? Smoke coming out of it yet?
Yeah.
I'm watching carefully for smoke. I hope it does, because this caused a lot of smoke to come out of my brain. I don't want it to be easy for you if it was hard for me. It took a lot more than one pass in order for me to kind of go, okay, I'm kind of getting this now. So don't expect watching me do this once. You're going to be like, oh yeah, I get this now. Okay. Well, let's proceed. Let's go look at what happens vertically then. We just were able to make a calculation based on breaking it into horizontal components. That's kind of cool. Just the fact that we did that alone allowed us to find the rotational speed of the crank arm. But does it make sense? The orange velocity of AB vector was connected to the crank arm, but now we want to, sorry, connected to the connecting rod. But now we want to see kind of what's happening to this. This is the ultimate rotation I want to know, is how fast is that thing spinning around, right? That's the part that's connected to the engine. And of course, just like we did a second ago, that's connected to this direction. So just like we wrote out our equation a second ago, we're going to do the same things. So I'm just repeating the same equation here. Velocity of B equals velocity of A. And notice I'm very careful. I'm not even finishing what I'm writing. I'm very carefully writing the original equation here. This is that original yellow highlighted equation. It's every problem you do is going to be based on this equation. But we're saying, oh, we only want vertical. So let's just consider what happens in the Y direction only. Okay, well, stare at the picture. Do we know anything? Do we know anything about any of those? What is VBY? What is it? How is velocity B moving in the Y direction? Well, I don't know the answer to it, but would you agree that I do know that it's actually the same as just the velocity of B, because it is going straight up. So like, it doesn't accomplish anything. Doesn't mean I know what it is, but like a second ago back here with X, we had to like convert it to get V of BA by using cosine. Well, this is going straight up thanks to where I drew it. So it's just the same as velocity. What else do we know? Nice job. A is moving to the right. It is not moving up at all. Therefore, it's nothing. Do you agree with that? So that's not good, because what about VB of A in the Y direction? Again, we have that drawn over here. That's this direction right there. It's like, how fast is that going? So I don't like this second equation because I have two unknowns in it. However, didn't I just get done figuring out VB of A? Didn't we just get done figuring that out a second ago? Like, just like a second ago, we rewrote this as velocity of B over A, but what would the modification be this time? It'd be the sine of 50, wouldn't it? Which then allows me to take this 0.67 that we just found a second ago and throw it in there, and then I'm actually going to be able to know the velocity of B. Isn't that cool? So if I just take 4.67 times the sine of 50, thanks to that 0, then I know the velocity of B now. Which is 3.58 feet per second. Again, I don't know what I'm being asked, but that feels important. Now, again, this is powerful. The piston had 3 feet per second, and we actually literally know the linear velocity of B. Now, it isn't going to be allowed to move in a line. It's not going to be allowed to deviate from that dotted circular path. But notice, interestingly, it's going faster. A was going 3. Is B going 3? No, faster in this particular location. Kind of weird. And again, just a second ago, did we not say that that velocity is equal to the angular? I want you to stare at this carefully. Just going to rewrite it over here so we have room. Didn't we just get finished saying that linear velocity is equal to angular velocity times radius? But I want you to stare at the picture. What angular velocity is that giving us? What radius is that talking about? Isn't B forced to stay on the circle defined by that radius right there? It's going around and around and around C, isn't it? So the angular velocity of this is B rotating around C. Again, I kind of like to write it like that. B as it rotates around C, B with respect to C. This is not what you would see in the book. They just say like CB. They just kind of write it randomly. And I get that because they're just saying the line we're talking about here is CB. And the radius, therefore, is also CB or BC or whatever you want to call it. How long is that thing? And we know that radius, BC, geometrically, we were told was 2 feet. 2 feet. So all I have to do is take 3.58, divide by 2, and actually know that angular speed now. The angular speed of B as it rotates around C then, 3.58 divided by 2 is 1.79. And that was something I wanted to know. Now, even though your brain is scrambled and you're not making great sense of this yet, that's pretty rad. I mean, we got the car moving here. Like, isn't this cool? Like, you probably can't do it on your own. But that 1.79 right there, remember 6.28 is 1 lap. And so this is like a third of that. This is like a third of a lap in 1 second, roughly, a third of a lap in the circle. It's like, that's got the car moving now. Isn't that cool that we actually turned linear velocity into angular velocity? So in the real world, I probably don't care about the green angular velocity too much. It's kind of talking about how that crank arm is moving. But I probably really care about that red angular velocity. Let's go back for just a second, since we can. And watch those things happening now. So stare at the green line for a second. Isn't it rotating? Do you notice sometimes it's not rotating very fast and other times it seems to be rotating faster? But the green line's rotating. We just calculated that. The blue line is rotating, right? We just calculated that too. In the end, that's kind of what we're doing. What we just did is the orange is not really the follower, it's the driver, but we got linear velocity over there with the orange dot, and we got angular velocity of green, we got angular velocity of blue. That's kind of cool that we can actually literally mathematically connect those two things now. Thanks to the just brilliant idea of somebody's part of breaking that confusing motion right there into first a translation and then a rotation. Wow, I never could have figured that out.
So the angular rotation or velocity of BC is going to be consistent. Doesn't stay the same.
That's not, so this snapshot in time right here is those two answers. If we let that move and we just said, okay, let's let 1 second go by and it went whoop and rotated into a new position, it'd be a brand new problem with a totally different set of answers. Even though 3 stays the same because we said, hey, let's not give that 3 an acceleration. Notice didn't say there's an acceleration. Unfortunately, it's going to have one in the next section. Maybe you'll get lucky and we'll run out of time. But if that's a constant 3 feet per second, that's not going to change. But B is not going to move at the same speed. It depends on where it is in the circle, frankly. Actually, I'll give you kind of a hint here. Let's say it was right over here. Does it make sense when this thing moves to the right, that actually doesn't move very much over there? So it's actually at its slowest right there. When it's in that position, it won't be rotating very quickly over there because it kind of hangs out really close to this. But if you draw it in a location where it's actually perpendicular to this, like right there, it's going to be hauling right there. It's going to be really fast when it's in that location. When that's 90 right there, it's going to really be flying.
Oh, this is because we're calling A is going to have a consistent velocity. So
That's right. And we're treating this like A just kind of goes right forever, but in the end, it's kind of going ding, 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 ding like this, and it's causing the other thing to go around in circles. And that's why cars can't really work on one cylinder, because if it gets to a certain spot, actually, if you have a 1-cylinder motor and the piston or the crank arm happens to be in the wrong spot, it isn't going to cause rotation. It just goes like this. But it's only if it's in some, and you can see where it is right there. But let's see, where can I draw this? Right there. If it was in this position, does it make sense? It doesn't want to go right or left there. Like, does it want to, if you put a velocity on this, does it want to go that way or does it want to go that way? It doesn't want to go either. Anyway, that's just time to kind of process, but that's it. You just need to practice that and get good at it. We're going to do one more example. It's not going to be any different than this. All right, let's do it. So I want you to actually pull your second one up. And the only difference with the second one is I made this one as easy as I could possibly make it in terms of complexity. Let's just go take a look at the second one and see if we can get it right. Same kind of drawing. However, find the velocity of C and the angular velocity of link BC at the instant when theta is 65 degrees and phi is 35. Notice in this case, I had to give you two different angles to tell you where everything is. You'll see why in just a second. But notice I put B on the circle up here in kind of just some random location. So I put it in a less nice location. And notice the driver this time is this. So this is the same exact math, but it's just backwards. This time I said the angular velocity of B as it rotates around A is 2 radians a second. So do you see how the crank arm is driving it this time? It's not the piston. So this is like the electric motor where B is going around that direction. And as a result, this is going to be over here going dum, 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 back and forth. You see that? Now I did say clockwise, so it's actually going this way, isn't it? Dum, 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 dum. So let's just start drawing some stuff in and try to make a little bit of sense of that. So if it's actually going clockwise, do you agree that this point B right here is actually going that way? That'd be the velocity of B. And I'll go ahead and fill this in. I hope this doesn't get in the way, but this thing is going this direction, 2 radians per second. That's its angular velocity. So that's the driver. And then the crank arm is the connecting rods over there making C. And do you all, again, also agree that that means C is going that way? Just trying to reason this out. Now, in this case, this is my own language to try to help. I mean, this is what made it make sense to me. B is the driver and C is kind of the follower this time. But fortunately, this isn't a new problem. It's the same exact thing. And so, of course, what we want to know is the velocity of C this time. Well, how do you find the velocity of C? The velocity of C, this is exactly what we just did a minute ago. The velocity of C, the letters are different, but the velocity of C, what you would like to know, is equal to the velocity of B plus the velocity of, let's see, is it B as it rotates around C, or do I have that backwards? Is it C as it rotates around B? Notice the letters are screwed up, so I find myself going, I don't know. Now I could go look at the previous formula and say, where was the A's and the B's? But again, let's try to reason this out for ourselves. We're saying B moves first. So this is first. Okay, what does that do to C? Well, let's say it moves to, we'll let it move to here, moves to right there. Well, then doesn't that cause C to do exactly the same thing? So it moves to right there. Now, can C actually go up there? Think about this. What does C have to do? It's got to stay in that right path, right? That right-left path. It can only stay horizontally. So can it actually go up there? No. Secondly, it's got to make this rotation. Oh, I got it backwards. So let's stare at this. In order to get back on track, once it gets there, do you agree that it has to follow this circle to get back to here? That's where it's actually got to go. So C first goes here, and then it goes here, and now it's kind of back where it belongs. So I guess that's actually C rotating around B. So no, I got it right. So this is correct. I sort of got lucky. It is C as it rotates around B. This hurts, doesn't it? Now, you could just sort of stare at this and say, well, you know, that was C and C is on top over here. Let's look at the previous problem. I could have said, I don't know, but back here, B was here and B was on top, and I could have just wrote it that way. But it's like, I'm trying to understand this deeper than that. So first it's a translation, since I wanted to know what's happening at C. So I said, what is happening with C? That's the interesting thing here, since B is the driver. So I say, well, first B gets to do what it wants to do. Since B is moving in this direction up here, then that means C is moving in the exact same direction first. But then secondly, we say, well, it can't do that. That doesn't make any sense. It's got to rotate back into position. And notice that rotation is actually going in this direction. It's actually rotating what we call positive. It's got a positive angular velocity to get back to where it's actually got to go. Go ahead.
This is just me trying to visualize this better.
Good job.
Can we say that C is rotating around B, and if C wasn't locked into a set path, that it would be rotating about B?
That's exactly right. If it was not locked into a set path, then it would literally fly up in the air in that dotted line. So if it wasn't hooked to something, it would just like be flying around in circles, you know, like having a rope attached to the end of this. If I start swinging it, it's just going to go wild and go everywhere. And of course, that's what we're doing in a motor, is we're trying to say, I'd like this linear motion to turn into rotational motion so I can accomplish something. In this case, I'd like this rotational motor to cause linear motion, and I want to capture it. I want it to get to go where I want to go. So I'm going to say, you know, put it in this pipe over here so it moves to the right, because I want to accomplish something. I don't just want it to flail around. Any other conceptual questions about what you're seeing there? Again, I don't mean you understand. You might not be able to formulate a question yet. But despite the fact that this is a different picture and even a different driver, it's still the same exact formula. It's the same exact math.
So the driver will always equal the follower.
That's exactly right. First, the follower. First, let's see. Yeah, I think you said that right. First, the follower will be equal to whatever the driver did. And notice those are linear velocities. That's why I had to draw it over here perpendicular. Did you notice I was careful to draw that 90 degrees right there? That's the direction it's going, thanks to this 2 radian per second clockwise. I know that's the direction B is going. Well, then if you want to know what C is doing, it's doing exactly what B is doing to start with. But then because of Ian's point, it's like, you know, could it actually go up there? Well, no, it's contained in this horizontal shaft, this horizontal cylinder. So it's actually forced to go right. So it can't be up here. How's it going to get back up there? Well, then it's going to have to rotate around this point. I guess I call that B prime. It's going to have to rotate in the, what direction is that? Positive. It's going to have to rotate in the positive rotational direction to get back where it belongs. So now mathematically, I have a way to do this. If I can figure out this velocity of B and I can figure out this rotational created velocity of C as it rotates around B, then I can add them and I'll have the answer that I want to know. First, a translation, it just moves, and then secondly, a rotation. Okay, good news. Now I'm just going to do exactly what we just did a minute ago. Now, all of these drawings that I just made to help you understand conceptually are going to be in our way because I got a bunch of geometry I've got to draw. So let's see if we can sort all of this out. My velocity would be back over there. So we said, okay, cool, let's do this horizontally and vertically. I don't know whether to do, you know, like what order to do this in. Should I be doing vertically first, horizontally? I don't know. I'm just gonna, maybe we'll get lucky and the first equation we write will be the right one. I don't know. So what am I going to do? Same thing I did before. I'm just going to rewrite the equation. Velocity of C equals velocity of B plus the velocity of C as it rotates around B. I'm just going to say, well, let's just focus in on the X's now. Go add those in later. And I'm going to ask the same question. Do I know any of those things?
Well,
Yeah, so look at my givens up there. This feels harder because I'm looking at it going, I don't know any of those. Now, would you agree that we agreed that C would actually be moving to the right here? Like that's the velocity of C. It's gonna go that direction, which actually is the same thing as the velocity of C and X because it's forced to move in the X, right? But I don't know that. I wasn't told anything. They didn't tell me anywhere the velocity of C is 19 or something like that. Last time we knew that was, oh, it's 3. I don't know that this time. That's actually what I need to know. What about the velocity of B then? Do I know that? I don't know that either. I know the rotational speed of B is 2 radians a second, but I don't know what the velocity of B is. This is not good. Like I sort of don't know anything.
Okay, that. And give break components.
Yeah, I do know some angles here. Let's go ahead and throw those in since we're sort of punting, saying we don't really know. This we're told is 35 degrees and the other one is 65 degrees. That looks about like the picture is drawn, right? But let's think about something we do know. Do we not know that velocity is equal to angular velocity times radius? So this time I was actually given over here an angular velocity of 2. And that radius that goes with that from A to B, I was told up here is 4. Aha, so that means the velocity of B then is actually 8 meters a second. Now, stare at the units. What is angular velocity? It was radians per second. What is 4? That was meters, right? So if you take meters times radians per second, that's meter radians per second, because radians don't exist, that's meters per second. So, okay, we actually know the velocity of B. Now, unfortunately, is that going in the X direction up there? No, but let's get a little more creative. Isn't this the velocity of B in the X direction? And wouldn't that, thinking of these as vectors, wouldn't that be the velocity of B in the Y direction? Now, do I know that angle up there? I find myself thinking, no, like you gave me 65. Can you work your way up to that location though? Now, there's a number of ways to do this, but here's one of them. If you know this angle is 65 right here, then that angle up there is also 65 if these two lines are parallel to each other. Now, do you have to memorize that? No, you could draw in this auxiliary line here. Since this is 90, then wouldn't this be 25? 25 and 65 is 90. But then isn't this a right triangle up there? So then if this is 25, doesn't that make that 65? So the geometry of these, you just got to get kind of creative and draw stuff in. So that means this angle is 65 degrees, but then don't we know this angle is 90? The velocity is always perpendicular to the radius. So if that's 90, then doesn't that mean this is 25? So now I know an angle in that triangle. Isn't that kind of cool? So I do know the velocity of B in the X direction. If I took 8 which actually is the velocity of B, but then modified it by the cosine of 25, wouldn't that be? And that's kind of cool because that's actually just a number, isn't it? It's like that's literally a speed. So it was not obvious that I knew that. Wow, was it not obvious? But I actually did know it. So that's just a number, but I'm still not very happy with my equation there because it's got 2 unknowns in it. So we already agreed we're not going to know this one. But the question is, you know, is this one, do I know this one somehow? the velocity of C as it rotates around B. The velocity of C as it rotates around B, based on the direction of travel in the picture we drew a minute ago, do you agree that it is this? It has to be 90 degrees. That right there, my friends, 90 degrees is the velocity of B as it rotates around C. I said that backwards. The velocity of C as it rotates around B. Again, I ask you, how did I know it wasn't over here? Isn't that also 90 degrees? The only way I know that is based on logic. And that's based on what I showed you a second ago. We said a second ago that first, this thing is going to go into this position. And then in order to get into that position, it's going to have to rotate. Didn't we say that direction? That's why I know what direction it goes. Otherwise, I wouldn't know. Now, the cool thing is, if you get this wrong, you'll get like the sign will be wrong, but you'll still get the number right. But it helps to draw this out, like to sketch it off to the side to make sense of that. So I'm correct about that. It goes in that direction. Well, because that's 90 and that red angle there is 35 degrees, then don't I know that this angle is, what is that, 55? And then wouldn't this direction straight up be the velocity of C as it rotates around B in the Y direction? And then to get over here, wouldn't that be the velocity of C as it rotates around B in the X direction? Now, I don't know anything that's going on down there. I don't know any numbers. But I could at least replace this statement right here, velocity of C as it rotates around B in the X direction. I could say, well, that'd be the same as the velocity of C as it rotates around B, but times the sine of 55 degrees, because sine is opposite and the opposite one is the X one. That doesn't really do me a lot of good. It's just that it, so I'm done here. I'm stuck. Like this has got two unknowns in it. I've got this unknown and I still have that unknown. What's going to happen in a second when I jump to the vertical equation? It's going to have the same components. So I'm going to be able to solve two equations, two unknowns. The first one we did, because of the really nice position I drew it in where it was 90 degrees, we were able to solve one of those equations because it was one equation, one unknown. But when it comes down to these problems, every time you just basically write out your horizontal equation, you write out your vertical equation, and you solve them. All right, let's try to tackle the vertical one. Sweet. What's happening vertically in the Y direction, my friends? Again, what do? I rewrite my equation. It's the same equation every time. It's the top equation. Velocity of C equals velocity of B plus the velocity of C as it rotates around B to get back into position. But I said, oh, I'm just working on vertical stuff. So put a Y into all of those. So sticking with the same thing we just did a second ago, we got done writing this statement right here. Well, couldn't I also rewrite the velocity of C as it rotates around B in the Y direction by saying, oh yeah, it's the same as the velocity of C as it rotates around B. It's just that that's modified by the cosine of 55. Now, why did I do that? Because now these have the same exact unknown in them. If we had left it with X and with Y in them, those are two totally different unknowns, but thanks to trig, they're the exact same unknown now. So these two equations can talk to each other algebraically. Does that make sense? What about the velocity of B in the Y direction? Well, from our figure up here, what's the velocity of B in the Y direction? Oh, that's 8, but multiplied by the sine of 25, because velocity of BY is across from 25, that's the sine. So just like in the previous problem, we did 8 cosine of 25. This is going to be 8 sine of 25. So at least that's a number. And then lastly, take a look at C. How is C moving in the Y direction? How's C moving in the Y direction? It's not moving at all, right? It's not allowed to do that. So that's kind of cool because then I can say that one's 0. So there's my 2 equations, 2 unknowns. Now, can I solve either of those like by itself? Stare at that a second. The answer is yeah, there is one of them I can solve by itself. Do you see that? The Y one. I don't need to solve 2 equations, 2 unknowns. Isn't this a constant? That's nothing. And that's just a number. And well, this just has 1 unknown. So I can actually solve. So had I written the vertical equation first, then I would have been able to, oh, I can answer that. That's kind of cool. So in the interest of valuing your time, if I solve that and get the velocity of C as it rotates around B as being 5.89. And then now that I know that, just like last time, if I go stick that in up here, does it make sense? The top equation that used to have 2 unknowns doesn't have 2 unknowns anymore. So if I stick 5.89 in there, notice I'm actually going to be able to find the velocity of C as it moves, and it moves in X. And of course, that's the thing I wanted to know, like how fast is that piston moving? This is really exciting. Like that, I'm now able to see what C is doing. I actually know how fast it's moving linearly. Remember, linearly, this B up here was moving 8 meters a second. So I wonder what C is doing. Your gut reaction might be, oh, it'll be 8 meters a second too, but no, it might be faster, it might be slower. If I throw that in up there, then C pops out as actually 12.08 meters a second. And this is actually one of the things I wanted to know. I'm going to box it instead of, so notice as interesting, it's actually going faster. Now, any of you water ski before? If the boat is going 25 miles an hour, are you as a water skier going 25 miles an hour? The answer is yes, if you're right behind the boat and just standing there. What happens if you start crossing the wake? You can haul ass, man. You can you can whip. And that's what we're talking about here. That's what's happening. This is being whipped. When can you really whip? When the boat does exactly what this thing is doing, which is make a right-hand turn. If you make a right-hand turn there and the skier goes that way, you really get whipped. Well, that's what's happening here. It's going 8, you're going 12. So it's kind of cool. Again, I want this to ruin your life. Other people are water skiing and you're hunkered over your calculator with full clothes on, with the hoodie on in the boat, making calculations about how fast the skier is going out there. Now, we're done. You know, it's like, have we answered all the questions it wanted to know? Let's see. Find the velocity of C. We found that. Now we said the velocity of Cx, but that's because it was stuck in X. We found it. It's 12. Amazing. And the angular velocity of link BC. Notice it didn't ask for the angular velocity of AC because we were already given, that was the driver here. So the only things that are really moving is this crank arm is moving, CB is rotating at a certain speed, and C is moving. So we just need the angular velocity of BC. So what's the angular velocity of BC? Let's go ahead and write that out down here. The angular velocity of BC. How do we find that? Well, we said before that velocity is equal to angular velocity times radius. But if we want BC, then we got to talk about how C is rotating around B, and this then would have to be the radius of CB that we're talking about. And then this would be the velocity of C, the linear velocity of C. So let's see, what do I know in that figure? Well, I know the velocity of C, we just got done figuring that out, was 12, right? Wait, that's not true. I got to be consistent. This isn't true. That's not the velocity of C, it's the velocity of C as it rotates around B. Do you agree with that? I actually did not make that mistake on purpose, but if you're talking about the angular velocity of C as it rotates around B, then you're talking about the velocity of C as it rotates around B. You see what I'm saying? So that was a goof on my part. And we did know that one time. Where did we know that? We figured it out. It was 5.89, right? So that's 5.89. And we know the radius of CB. We haven't looked at it yet, but that was one of the givens. The radius of BC or CB is 10 meters. That's a lot longer. That actually sounds like a skier, doesn't it? 10 meters, 30-foot rope. This is meters per second, since that's a linear speed. If I divide meters per second divided by meter, I get nothings per second. And so that angular velocity of C as it rotates around B. And again, think of this as a skier, and that's the rope. That's kind of interesting to think about what that angular speed of the rope would be, isn't it? So I get 0.59 when I divide, as you know, 5.89 divided by 10, 0.59 radians per second. And so that was the other thing that I wanted to know. So your job then, if I was you, before I tackled the book questions directly, I would re-look at these, particularly this one. I'd re-look at this one like from scratch. All the 90-degree angles in here are not insignificant. I'm going to go back and fill them in. This 90-degree angle right here, if you don't understand that that velocity has got to rotate at 90 degrees, same thing up here. This was 90 degrees. If that 90-degree thing doesn't make sense, you're going to have an impossible time tackling all these angles and so forth. But the backbone of these equations, the backbone of this beauty, this piece of glory right up here, everything came out of that. And then looking at it horizontally and vertically independently, getting two equations and then just dealing with them algebraically. Is that two equations, two unknowns? Is one of them one equation, one unknown? And then converting from linear to rotational velocity. This last equation, or the one that we had back up at the top, but this last equation allows us to, if we know linear velocity, we can always turn it into rotational. If we know rotational, we can always turn it into linear. Unbelievably cool, but extremely painful. The last thing I would say, and I'll shut up, would be take the time with these problems rather than just writing those equations down and trying to solve them. Because remember, if you get the direction those arrows are going, I got this arrow going that direction, I got this one going that direction. If you get those backwards, it's going to make the whole picture look weird. Take the time on a piece of scratch paper off the side to literally draw this first. Okay, I want to know how C is happening. Well, then first, it does exactly what B did. And so in this case, we said, oh, look, B moved up and to the right. Okay, well, then C is going to move up and to the right. Draw that in, draw that thing in there. And then say, okay, now it's got to rotate back into place because it's not able to actually do that. And then literally draw the rotation. So you can literally get these arrows going the right directions, kind of make sense of the picture. And in the end, those arrows probably not move, probably those two arrows not being horizontal and vertical will take trigonometry to make them horizontal and vertical. And then you'll be able to write these equations down here that allow you to answer this question. Again, who thinks of this stuff? It's like one thing for you and I to like follow someone else's lead, follow a map to the waterfall, you know. But some person had to be the first person to figure this out. It's like, as I said, I found this really hard just to follow, let alone invent. Who's this smart? What year was this done? Guarantee this was done before calculators, which blows my mind. With respect to velocity, don't have anything else to show you. What I'm going to show you on Thursday is a neat method that allows you to kind of do what we're already doing here. So we're going to stick with velocity. We're just going to make some of these calculations in a different way. So fortunately, in a sense, Thursday won't be terribly new in that sense. We're going to practice this some more. We're just going to get part of our information here in a different way. And then the first part of next week, which is the last week of class, we'll go into acceleration. If you come Monday not being done with this, you're going to be in a world of hurt. So be done with this, like feel as good about it as you can get. And this last test is really, I mean, you can see how long this takes. It takes an hour just to do one question here, and we've only done velocity, and we got to do acceleration. It's like one problem represents this whole section. So my advice would be come back Thursday with really good questions about what you're not getting correct so that I can help you conceptually see where you went wrong. Try to make your work as slow and clear as possible. Try to make it look like mine, not that mine's perfect, but at least you can see everything that I did. Nothing is erased and so forth. Let me help you troubleshoot if you're not getting the answer right. All right, thus was ended Tuesday.